Chapter 3, Section 4 is on polynomial functions and graphs. The first one asks us to graph the polynomial function y equals x to the third minus 3x squared minus 6x plus 11. Now the way to do these without having to spend a ton of time plotting points and factoring and so forth is to understand some of the basic rules for polynomial functions. The leading term tells you a lot about what the graph is going to look like. The leading term here is x to the third power. Now, since this is a positive leading term, positive leading coefficient, that means whatever the graph is, it's going to end up going to positive infinity. Now, another thing you can tell about the graph just by looking at that leading coefficient is that it's a third power. That means this graph could go in 3 directions. It could go up, down, and up, or it could go down, up, and down. So a basic cube function is going to look similar to this. And because this leading term is positive, it's going to end going in a positive direction. It's going to go up. If you look at a graph from left to right and it's a positive leading coefficient, then the graph is going to end up going to positive infinity. So out of the 3 choices that were given here, the first 2 look like they could be x to the third polynomials, but because our leading term, leading coefficient is positive, this is going to be the correct choice out of all 3 of those. I'm going to choose B, check your answer. So again, notice I'm not basing this on making a table of values. I'm just basing this on understanding what that leading coefficient does to the shape of a polynomial function. If this were an even one or 4th power, 5th power, 6th power, if the leading coefficient is positive, that graph is going to end up going in a positive direction on the right-hand side of the graph. You can also check this with a graphing calculator. With a graphing calculator, you can confirm this, although again, it's not necessary if you understand the patterns for any of these polynomials. If it's a leading coefficient is positive, it means it's going to end up on a high note. It's a 3rd degree polynomial, so it could go in 3 directions. It could go up, or it could go down, up, down. So it goes in opposite directions on the right hand and left hand side. If you use a graphing calculator, go ahead and press the y equals and enter the polynomial function. And then I always start off with a standard zoom, standard graph paper, and you can see the graph of this polynomial. It doesn't look exactly like the one that's in the picture, because if you notice the scale has been changed and it's indicated below the graph. Now this first part here, the negative 10, 10, that is saying that the x goes from negative 10 to positive 10. And then by negative 100, positive 100. That means that the y value on the graph goes from negative 100 to positive 100. Now to change that on a graphing calculator, press the window button and notice if you do a standard zoom, the x-min and x-max is negative 10 and positive 10 with an x scale of 1. That's what's showing up here on my math lab. Now, negative 100 to positive 100, that's your y min and y max. So I'm going to change the y min to negative 100 and change the y max to positive 100. And the y scale is 10. So I'm going to change that to 10. I'm using what the information given on my math lab. And now when I just press graph, you should see a different looking graph, a graph that goes up, down, and up. It's a 3rd degree polynomial. The leading term is positive, so it's going to end up on a high note. Because it's an odd degree polynomial, it's going to go in opposite directions. On the left side, it goes down. On the right side, it goes up. Again, you don't need a graphing calculator. If you understand that concept, then you can make your decision rather quickly. Now look at number 2. For 3.4, number 2, the comprehensive graph of a polynomial function is shown. How many real zeros does the function have? Real zeros would indicate where the graph has an x-intercept. This graph only has an x-intercept at one location. So the number of real zeros is the same thing as number of x-intercepts. This has one x-intercept, so this has one real zero. And we can check our answer for that one. Again, doesn't rely on using any algebra here. It's simply looking at a graph, looking at where the graph crosses the x-axis. It crosses the x-axis in one spot. That's your one x-intercept. That's how many real zeros the function has. Question number 3. We have this polynomial function and we have a graph. The graph is going to help us factor the polynomial function. Notice that this graph crosses the x-axis, or actually touches the x-axis right here at -5. It crosses the x-axis at 0. It crosses the x-axis at 6. Now, each of those times where it crosses the x-axis corresponds to a factor of the polynomial. If it crosses the x-axis at +6, that means x minus 6 is a factor. If it crosses the x-axis at 0, that means x is a factor. If it crosses the x-axis at -5, that means x plus 5 is a factor. This is a fourth degree polynomial. Fourth degree polynomials can have 4 factors. Now we can see 1, 2, 3 of them are listed here, and the fact that the graph touches the x-axis at -5, that's going to indicate that you have a repeated factor. Now, the way you can approach solving this problem, if you know that these are the zeros of the polynomial function, the zeros are -5, 0, and 6. We can use that to factor this polynomial using synthetic division. Now our polynomial function was x to the 4th plus 4x to the 3rd minus 35x squared minus 150x. Now hopefully you noticed that all of these terms have an x in it, so that's going to be a common factor. Factor out the x out of all of those and you get x to the 3rd plus 4x squared minus 35x minus 150. Now the way you're going to factor the remaining part is given these other zeros of the polynomial. We know 6 is a 0 of the polynomial. We're going to do synthetic division with a 6 using the coefficients of this large factor, 1, 4, -35, and -150. So we're going to do that and get 60 here, 25, 150, and 0. Okay. So 6 is a 0 of the polynomial. That means x plus 6 is a factor. So x is a factor, x plus 6 is a factor. Now we can factor what's left here. We also know that -5 is a factor. So we're going to continue the synthetic division with -5. And you see how we get another remainder of 0? So since negative 5 is a factor, negative 5 is a 0, x plus 5 is a factor. And then also what we have left here, the 1 and the 5, that corresponds to another factor of x plus 5. So this polynomial function can be factored as one factor of x, another factor of x plus 6, and another factor of x plus 5, that quantity squared. We say that's a repeated linear factor. And check our answer. Okay, sorry, I did make one mistake here. This, I apologize for this, this should be a minus 6. X minus 6 is a factor, not the x plus 6. I want to make a, oops, there we go. I was rushing through that. I apologize for that mistake. But again, this should be x minus 6. This should be x minus 6 as a factor. If you caught that before me, good job. You're paying attention. Okay, so this should be x minus 6. If it's 6 in the box, that corresponds to a factor of x minus 6. Okay, so the way we use the graph is each time the graph crosses through the x-axis or touches the x-axis, that corresponds to a 0. It crosses through at 6, 0, and negative 5. We factored out that common x, and then the remainder we use synthetic division to break it down into the other factors.